Okay, I think it's recording now. And it's picking up the audio now. Someone speak. I don't think it's picking it up. Give me 1 second. Uh, okay, speak now.
Hello.
Okay, now it
Hello.
is. Yeah, now it is. Okay. So let me just share my screen. All right, can y'all see? Can y'all see?
Yeah. Yeah. I think so.
Okay, just give me 1 second. All right. I mean, we already did the exams, but I did it with the people in other servers, so I guess we could just redo it. Let's see. Fuck. Oh. Oh yeah, also remember to check your guys' seats, or else y'all are just gonna delay everyone. Alright, so again, I will just do. Okay, and then we're not doing that. That. Okay. So, this is one of the questions. This is for
Oh,
this.
sorry. Could you landscape, bro?
Oh yeah. Let me just move my book out the way, because this iPad is too fucking big. Uh, Alright, you see now?
Yep. Thank you.
Yep. Alright, so this is saying that we have an execution cycle, right? And we need to figure out the values at each instruction and then answer these questions down here where it says total data memory access counts, count of each instruction type, uh, the values of PC, and then the value of the CPI. So let's go here. It says consider the following executable loaded into main memory with offset 0012. Once we see it's offset 0012, we're immediately just going to go right here. What the fuck? 0012, right? That's the first instruction. And it says assume R1 is equal to 3, R2 is equal to 2. That. Executing on a 64-bit system. So this is how we figure out what we're going to increment by it, right? Where we take number of bits in the 60 in our system, we take it and we divide it by 8, right? It's going to be 8. Same thing as like if we do 32 divided by 8 on a 32-bit system, that's 4, so you increment by 4. 16-bit system divided by 8, that's what, 2, right? So that gives you what you're going to increment by. So don't forget that, or write that down in your books or whatever. To find what you're going to increment by on your PC, take the amount of bits, divide it by 8, and that will be what you're going to increment by. So from that, we can see that we're incrementing by 8, so that's going to be 0012, 0028, sorry, 20, 0028, 0036, and then 0044, right? And then I guess we can also just put on the actual extra part. I think that's 52. Okay. You don't have to put that extra part there, but just in case they ask you for like what's the value of PC at the end of the fetch stage of the last instruction, that would be 0052. Okay. So then we now have to fill out the values, right? But we first have to read this next part where it says answer at questions. Assume each data memory location has a value of 2, and if not provided or stated, general purpose register is initialized to 1. Again, so it's saying assume each data memory location has a value of 2. So let's say in our program, memory location 3 pops up. That means that that contains 2, right? Or whatever value that may be. Let's just say it's X. That contains 2. And then for any general purpose register where the data is not provided, it's initialized to 1. So for any Rx, it's equal to 1 unless it's provided. Okay. So from here, we're saying what is the value of PC at the end of the exec stage for this instruction, right? And let's see. So we have this instruction here. We have R1 and R2. If they're equal, then we branch to X, right? And we see here that 2 is equal to 2, and R1 was not initialized, so its value is 1. So they're not equal, and that means at the end of the exec stage, the PC will not be incremented uh, to whatever value is X, right? If they were equal, then the answer would be X, right? Or, sorry, not X, it would be 0044, because that's where X is, right? But since it's not, then it's going to be whatever value was incremented to in the fetch stage. And that value was 0020. So the answer here would be 0020. Okay. Now this question, I didn't get to ask him about. I was really confused about this question because for this answer, he put 1. But I'll tell you why I don't think it's 1. He would probably disagree with me, but again, I disagree with him, so. But it says here, this is the next instruction, and it says that for general purpose registers are initialized to 1 if they're not stated. But here it was stated that R1 is equal to 3, meaning that here we're not dealing with R1, we're dealing with 3 R2. That's what it looks like, right? But we have to figure out what the value of the MDR is after the exec stage, meaning the data that we retrieved from address 3, right? And the data of address 3, we don't know because that wasn't initialized. And it says assume each data memory location has value 2. Meaning that the data inside of address 3 is value 2, and we're putting that data into R2. And we do that by going from the data line in memory, putting that data onto MDR, which just says value of MDR after exec stage. Actually, after exec stage, hold on, let me think.
Can I just interject? In class, he said
Yes.
it's not supposed to be
Stage.
exec, it's supposed to be
Yeah,
mem.
yeah, it's supposed to be mem, sorry. So this is after mem stage, right? Meaning that the value is put on the data line and put into MDR, right? And then from there, that should store the data that was in 3. And again, we know that the data memory location has a value 2. That's why I think the answer should be 2, but he says it's 1, which to me that doesn't make any sense because it's only 1 the data if the data type wasn't stated. Sorry, the value of the register wasn't stated, then it's 1. But here we're stating it, so like that doesn't really make much sense to me. So that's why I put 2. Y'all can go with 1 if you want, but that just makes more sense to me. So yeah, and I really don't understand how we got 1, so I couldn't even explain that anyways, because it just doesn't make sense. Because I guess if he's just going off a general purpose register, that since we don't have the value of 3, that means we can't have the value of R2. but that's kind of contradictory based on the question, so I don't really know. Anyways, then we have R4, right? Which from here, we know that R2 stores the value 2. So in this R-type instruction, that's just going to be 2 plus 2. So then R4 stores 4, right? And then let's go to the question here. It says value of MAR during the write back stage, right? That'd be the write back stage of the R-type instruction. But we know that R-types do not have mem stages. So from the fetch stage, the MAR never changes, right? Because we're not going back to memory. So that means that we're still just, MAR is still just going to be holding whatever was an MAR previously, which was 0028, right? Which is when we were fetching the instruction, right? Because in exec of the R-type instruction, we only use ALU. We don't use MER, we don't use MDR, like all that stuff. We use the ALU and the Z register, and then we put that whatever's in the Z register into R4 in the write back stage, right? So the MAR here, I believe, would just be 0028. Okay. And then here it says R2 into R4. We know 4 is number 4. So we're saying 4, address 4 into, sorry, we're taking R2 and putting into address 4, which we know R2 is 2. So we're putting 2 into address 4, right? And saying what is the value of the MDR at the end of mem stage, right? So here we know with with store types, when we're in the exec stage, MAR we store the address that we're going to, control stores write, and MDR stores the source register, right? We take that all the way to memory, and then we store that. We store whatever is an MDR into the address that's an MAR, right? That'd be the value of MDR at the end of the mem stage. Just because you put it into, that data, that doesn't mean that's still not an MDR, right? So I believe that would be R2. I think you could put R2 or 2. That's whatever you want. But just to be safe, I would go with 2
Wait, why is it 2? Not 4?
because R2 stores 2.
I see. Okay.
Yeah, and we're taking with that the MDR stores R2. Okay. And then here it says, what is the value of Z at the end of the fetch stage? Right? So we know this is an R type, and this R type utilizes the ALU and the Z register during the exec stage, right? So you can think of the Z register as a general purpose register, where once it's filled, the value of it's not going to change until it's filled again or overridden, right? So it's saying what is the value of Z at the end of the fetch stage? The fetch stage we haven't used the Z register yet. That's an exec stage. Fetch stage, all we've done is grab the instruction and we're getting ready to decode it, right? So we have it in this instruction here at the end of the fetch stage, we have not used Z yet, right? So now we have to think to ourselves, what does Z store? It can either be storing nothing, or it could be storing something from a previous R-type instruction in our code. So let's see if we have any R-type. This is an S-type, and we have here's an R-type. This R-type did R2 plus R2, stored that into the Z register, and then from the Z register it got stored into R4. But just because it was stored into the Z register doesn't mean that it just lost its value, right? 4 went into R4, but Z still holds R4. Sorry, still holds 4, right? And from here, our Z register hasn't changed at the end of the fetch stage yet. And that's why from that, our answer here would be 4, right? If it were to say at the end of the exec stage, what is the value of Z at the end of the exec stage of this instruction? It would have been whatever R4 is plus R2, which R4 is 4 and R2 is 2. So that would have been 6. But because it says at the end of the fetch stage, then that means it's going to be some previous value because we haven't utilized the Z register yet. That's why. And then here it says for above execution, calculate the total data memory access count. Right. So what this means, you can think of this as just how many. Actually, I'll do this point first because it's easier. Because if I do this one first, it's easier to explain this one. So total memory access count, you could think of that as just how many times we've accessed memory in our instruction, right? And we know we access memory every time that we run a fetch stage and every time we run a mem stage, right? Because in both of these stages, we have to go to main memory. Okay? So basically, every instruction is going to have a memory access count because every instruction has a fetch stage, but not every instruction is going to have a mem stage. Meaning that there's going to be some instructions with 2 memory access count and some instructions with just 1 memory access count. From that, we know that L type is fetch, decode, exec, mem, write. Store is fetch, decode, exec, mem. R is fetch, decode, exec, write. And then J is fetch, decode. Branch is fetch, decode, exec. Right? And let's go with our counter here. So we see that jump, it has 1 fetch stage, no mem stage, so that's going to be memory count of 1. Branch has 1 fetch stage, no mem stage, so that's going to be a memory count of 1. R type has 1 fetch stage, no mem stage, that's a memory count of 1. And then L and S type, they have a fetch stage, but they also have a mem stage, meaning they're going to main memory twice. So then both of these are going to have a memory count of 2. And then from this, it's asking what is the total memory access count? Meaning how many times have we gone to main memory in our program? So from that, we can kind of just count how many instructions we have, but then count twice for load and store because they go there twice. So here we have a branch, that's 1. Here we have a load, that's 2. Here we have a R, that's 1. Here we have a store, that's 2. And here we have an R, that's 1. So from that, that's 1 plus 2, that's 3. Then 4, 5, 6, and then 7. So your answer for total memory access count, that's just going to be 7, right? Because we're accessing main memory 7 times. Okay. And then for total data memory access count, that's just referring to how many times in your instruction code or in your program has there been a memory cycle, right? Where in your memory cycle, you're accessing actual data, right? Whereas in the fetch stage, you're just accessing addresses, right? In your mem stage, that's when you're actually dealing with data. Where with load, you're grabbing data from an address and putting it into a register, or with store, you're grabbing data from a register and putting it in an address, right? So that would be our total data memory access. We're saying whenever we have a mem stage Did I forget an R? Yeah. We increment by 1, right? And the only instructions that can have a mem stage are load and store. So this question is equivalent to just saying what is the total count of load and store instructions, right? And from that we would say branch, that's not a load and store. The second instruction, that is, let me just get rid of that. That is a load. Third instruction, that's an R type. Fourth instruction, that's a store. Fifth instruction, that's an R type. So in total, we have one load and one store. We add those together, and the answer is going to be 2. Because combined from this whole program, we only have 2 memory stages. So that's why our answer is 2. Any questions about that? Okay. And then from that, we say for above execution, provide the count of each instruction type, right? We're just saying we have 5 different types of instruction types. We have load, store, R, J, and branch, right? And that's basically just asking us to count. I hope everyone can count here. So we're just counting. We're branch. It's just one branch instruction. So we just go over here. Load, just one. Store. Let's see, looks like there's just one. R type, there is 1, 2. That's 2. And then there's no jump types, right? Because if it was a jump type, it would be, what, JMP, I think. So there's no jump types. And that'd be your answer for this. You can include jump 0 if you want, but I don't think you need to. Because in the answer, I think he just included load store, R type, and B. So I don't think you have to include J.
I think he said don't include J because you're gonna get points taken off.
Really? What the fuck? Okay.
Yeah.
Bro, the fuck is wrong with him?
Alright. Never mind. Do not include J. He actually said that? Actually crazy.
Yeah, I heard him say that.
Yeah. Okay. And then it says here.
Also, it says in the line it says executed code, so don't include a line if it's not executed.
Yeah, I guess.
I guess. Jesus Christ, man.
And then here it says, for above execution, now assume R1 is equal to 1 and R2 is equal to 2. Provide the value of PC at the end of exec stage for the first instruction. So it's saying that R1 is equal to R2, right? Because they both have the same value. And for the first instruction, it's saying we want to branch to label X if R1 and R2 are equal. And in this situation, they are equal, so we would have to branch to label X. So it's saying provide the value of PC at the end of the exec stage, right? And that's where we would do our jump, right, to our next PC value. So if this was equal, then we would have to update our PC at the end of the exec stage of our branch to the value of label X. And we see here the value of label X right here is 0044. So your answer here would be 0044. I don't know, you probably get points off if you just put X, so I would make sure when you start your question to put your PC values on the left side. And again, to find the incrementation, you just go to your system, take the number, divide it by 8, and that's it. Any questions about that?
Can you have like less than?
What?
Can you have like a 4-bit system? No, right?
I don't think so. I think the least he can give is like an 8-bit. I don't think you can really increment by decimal. That wouldn't really make. Okay, and then it says for above execution, now assume R1 is equal to R2, provide CPI. So I believe the CPI is the number of cycles over the number of instructions executed, right? And it's saying, assuming that R1 and R2 are equal, what would be the CPI of that program? So if it's equal, we're going to run this line of code, but then we're also going to branch to X. So that's one line, that's one cycle. So right now the instruction count is 1 and the cycle count is 1. Then from there, we're going to go down all the way to here and skip all those lines of code. And then we're going to run this line, which that's one cycle and one instruction. By cycle, I mean the actual cycle itself, where this is an R-type cycle, so that's going to be fetch, decode, exec, and write back. That's one cycle. And this is one this is one instruction. So from that, we have 2 cycles and 2 instructions executed. So that's going to be 2 over 2. So your answer is 2 over 2 is equal to 1. Your CPI, since we're on I forgot the name for it, single something processor, I don't know. Your CPI is always going to be 1, but he says show your work. So I don't think you can just put 1. You might get like a point for that or something, I don't know, because it's just show your work. Maybe 0 points, I don't know. But that's the number of cycles over the number of instructions executed, which is equal to 2 over 2. And from that, that's equal to 1. So remember to show your work.
What's a clock?
What is a clock?
Not like the physical thing. Like, like I thought it was clocks per instruction. Is it not? It's cycles?
I think it's cycles per instruction. Is that?
Okay.
I don't know. I can't remember. Isn't it like clock cycles? I don't know. Something like that. But just know it's the number of cycles over the number of instructions executed. Alright, is there any questions about any of the answers here? Alright, so I guess we can just go ahead and go compare them. So, let's see. And now again, I said that this one was R1 or 1. I don't understand why it's R1 or 1. It should be 2 because again, R2 is filled with 2, and then R4 is filled with 2 plus 2, which is 4, which is later proven at this answer here, 4. So that should be 2. So I don't know. Hold on, someone added to me. Yeah, CPI is clock cycle per second. Yeah. But that's why I'm saying that this answer kind of contradicts itself. Because if it's 1, then how is R4 4? Then wouldn't it be 2? And then this answer here would be 2, not 4. So I don't know. I don't know if he made a mistake there or like, I have no idea. But we were correct here. We got the correct answers here. And let's check here. We got 2, 7. He did not include the J. But he put conditional branch. So I would write that, because why not? And then 0044, which is the value at X. Right there, 0044. And then 2 divided by 2, that's equal to 1. You don't have to rewrite the formula. Just put 2 divided by 2, that's equal to 1. Okay. What the fuck just happened? Okay. Alright, is there any questions about that? And then fall 2022. Man, I wish this exam had cash. It's gonna be. Okay. Okay. So this one here. This question's 48 points. Damn. I don't even know what he's gonna ask tomorrow. But whatever. I mean, he doesn't really have much to ask us, so I wouldn't be surprised if he gives us this, and then just like this. I wouldn't be surprised. But one of the questions are different, where it's like give the memory string or something. I don't know. Anyways, first things first. It says the following program is loaded into main memory with offset 0016. Immediately once we see that, we set the initial instruction to 0016. He provides this for you. So I wouldn't be surprised if you didn't fill this, he would probably give you points off. So don't forget to fill that. So 0016, and it says and will execute on an 8-bit architecture. So that answers your question. I forgot who asked it. 8-bit, right? 8 divided by 8. Hope you all know that. That's just 1, right? That means we're going to increment by 1. So that's for 0017, 0018, 0020, 021, 002, 0023. And then let's just in case, 0024. Again, he said that you don't need to do that. But if he gives a question like, what is the value of PC at the end of instruction, of the fetch stage of instruction 8, the answer would be 0024. And you know that because you put that there, right? Someone's typing. I don't know if they're typing by mistake, but anyways. So you just divide by 8 always, right? Yeah, you always divide by 8 to figure out what you're incrementing by. Write that down in your notebook. Please do not forget it. Just divide by 8 and you'll know what you're going to increment by. That's it. So it says assume each data memory location contains value 18, right? So for any data memory location X, that's gonna be 18. And each register, if not provided, has value 2. So for any value Rx, voice crack, that's just 2. Okay. How do you know when the instruction isn't finished? Like when you went to 0024? How do you know when the instruction isn't finished? What do you mean? He'll never ask. He'll never ask what is the value at the middle of the fetch stage. It's either at the beginning or the end. So we know
Oh, okay.
PC is increments at the end of the fetch stage, not at the beginning.
Gotcha. Thank you.
Yeah, no problem. So from there, it says provide the value for PC register during the exec stage of instruction 4, right? So we're in the exec stage. That means that we've already done the fetch stage. So this is kind of the same thing as saying at the end of the fetch stage, right? Depending on the instruction. If it's like, let's say, a branch, that might be a bit different. But anyways, so for instruction 4, 1, 2, 3, 4, right there. It says provide the value of the PC register during the exec stage. So let's see, does our instruction have to do anything with PC? It does not. And at the end of the fetch stage, that means we increment to the next instruction for the PC, right? For the computer to read later on. So from that, since we're already done with the fetch stage, and our type doesn't do anything with PC during the exec stage, that means that PC has already been incremented to the next instruction, which we know the next instruction from our PC on the left side is 0020. So our answer is 0020. Okay. From that, we say provide the value for the MAR register after the exec stage of instruction 4. So we're still at instruction 4, and we're saying provide the value for MAR register after the exec stage of instruction 4. So let's look at R2. It's doing R2 minus R2, right? We already know R2 minus R2, that's just going to be 0, right? But, again, this is an R type, so it has nothing to do with MAR in the first place. Kind of tries to do a trick question here where you might think, oh, it's MDR, that's going to be 0. We're not messing with that. We're on MAR, right? And since the exec stage has nothing to do with MAR or MDR, as a matter of fact, because our types, it loads into the Z register, and then from there loads into your source register. In this case is R3, right? And it's saying provide the value for MAR register after the exec stage of instruction 4, meaning fetch is already done, decode is already done, and exec is already done. Within those stages, MAR is only changed during the fetch stage. What is it changed to? We know that what is changed to whatever value was in the PC during the fetch stage. That value would be what instruction we were at, which is 0019. So the answer here would be 0019. Because again, during the fetch stage, we put the value in PC into MAR, set the control to read, head over to main memory, grab that instruction, put it into MDR, then from MDR we put that into IR to be read, and then we and then we increment PC. Just because we increment the PC doesn't change the value that was in MAR. So MAR still holds the instruction that we wanted to execute at that line. And that instruction was 0019. Okay. Now let's say if it said MDR, then your answer would be R3, R2, R2, right? Because that's the instruction we grabbed from the main memory, put it into MDR, and then from there it was put into IR. So again, if it said MDR, that would be the answer. Okay. Any questions about that?
Wait, why is it the instruction? Sorry?
Because this is an R-type instruction. The instruction was R3, R2. And we know with R-type instructions, we're never dealing with memory. It's just fetch, decode, exec, write back, right? And the only time MAR is touched within those stages is in the fetch stage. During the fetch stage, the first thing we do is set the value of MAR to the value in PC, set the control to read, head over to main memory, grab the instruction at that memory address, put it into MDR, and then from there put it into IR, and then we increment PC. But that was the only time the value of MAR was changed to what instruction that we were currently at. And the instruction that we were currently at for instruction 4 was 0019. And that's why MAR held 0019. Does that make sense?
Yeah, okay, that makes sense, but why the instruction? You wrote the instruction, or is that the next one?
Yeah, I was saying if it said provide value for MDR register, then it'd be the instruction.
Okay.
Because we take the instruction from main memory, put it into MDR, and then from there we put it to IR to be executed. But originally it was an MDR, right? And MDR holds that instruction. From there, it says provide value for MDR register at the end of the mem stage of instruction 5. So instruction 5 says 18 to R1. So R1 looks like it was never touched, meaning that R1, if not provided, has a value 2 for any register, right? So that means that R1 is equal to 2. And we're storing the value 2 into address 18. So it's saying provide value for MDR register at the end of the mem stage, meaning that we have taken that taken that data from, actually, that's a store, right? Give me 1 second. Store, right? So the end of the mem stage, remember that in exec stage, we put 18 into our MAR, we put control to write, and we set MDR to R2 or the value of 2, right? And then from there we go to main memory, put whatever is an MDR into the data storage of whatever address is an MAR, right? So from there we know that the MDR is going to store our source register. So I think the answer would just be R1 or 2. I think you could put either one of those as an answer, right? Just to clarify, but MAR is always a mem address and MDR is data. Yeah, so um, uh, MAR stands for memory address register and MDR stands for memory data register. So MDR only deals with data and MAR only deals with addresses. That could be the address of an instruction, the address of data, stuff like that. Always fetch. MAR is always going to store the address of data, and then like exec or mem, MAR is going to store the address of what we need to either store into or what we need to load from. Right? Then here it says provide operation and operands for instruction 8. Let's go to instruction 8. It says R2. It says address 16 loads into R2. So let me just write it down here. All right. We know that our operation is a load type. So operation is a load. Our operands are of course the destination and the source. Right. So our source is going to be address 16 and our destination is R2. And that would answer what are the operation operands for instruction 8. Okay.
What if it's an R-type instruction?
Then I think you would just have, so you would still have one destination but two source. So let's say if it was register 2 and 4, it would just be source R2, comma R4, something like that maybe. Any questions about that? If it was a branch though, I have no idea. Because you would need to have the operation, actually no. Yeah, you would have to have the operation, then you would have the source registers, and then finally you would have the destination register, meaning that if that's true, then you go to that destination, I guess. That's my guess. I have no idea though.
What about a jump?
Jump. I think that would just be one. Huh. Actually. Oh, branch type, source, destination. Yeah. So that's what I was talking about. But jump, I'm guessing that's just destination. That would be it would be the operation would be jump, and the destination would be whatever label you put on.
But doesn't the operation depend on? Oh, never mind. It doesn't. Never mind.
Right, and then from there it says provide jump doesn't have exec so no operation. Actually yeah, I think so. Because it just has decode, and then in that decode stage you just increment PC to whatever that is, right? No. And decode that's no. Decode that's when you're identifying the operands. That's not an exec. That's done in decode. So that doesn't mean that there's no operation. Operation would be jump, and the destination would be whatever the label is. Yeah. Okay. And then it says provide value for PC register at the end of exec stage of instruction 7. So PC register at the end of exec stage, instruction 7. So we have a branch, and we're saying branch on not equal register 3 and 0. So are we saying is register 3 equal to 0? Right? If we go up 2 lines, we see that R2 minus R2, that's obviously going to be equal to 0. And that's stored into R3, meaning that R3 is equal to 0. So we're not going to do a branch here because it's saying we want to branch if they're not equal. If they're not equal, then we're going to branch to label Y. But since it's not, we don't. Okay. It says provide value for PC register at the end of exec stage, meaning that fetch has already been ran. And inside of fetch, PC is incremented to the next instruction. And since we're not going to label Y, that means that PC is still going to be pointing to the next instruction. And that next instruction is 0023. So your answer would be 0023. And then it says provide the total memory reference count. Remember, that's just counting every instruction, but counting load and store type twice. So we have, it'd be 2, 4, actually no, sorry. Remember, I actually didn't even bring this up. This right here, this is not a load type. Looks like one, but load immediate is actually an R type, right? And this would only have one memory reference count. Trick question. Because we're not dealing with memory. This is just an immediate value. The only thing we're doing here is fetch, decode, and write back, I think, right? I'm not sure. No, actually no. Fetch, decode, exec, write back because it's a R type. Fetch, decode, exec, write back. That's all we're doing. We're fetch, we fetch instruction decode, we tell what the operation operands are.
What are they?
Sorry.
What are the operands?
Operand, the destination would be R3, and then the source would be the immediate value 16. And then the operation would be a R type, right? And then in the write back stage, we just take whatever was put, sorry, in the exec stage, we put immediate value 16 into register Z. And then from register Z, it goes into R3 during the write back stage. Okay. So this is an R type. We never went to main memory, so that's going to be a memory reference count of just 1. Okay. So that's 1. This is 2 because that's a load type. This is 2 because that's a store type. This is 1 because it's an R type. 2 because it's a store type. 1 because it is an R type. 1 here because it is a branch. And know that it says branch on equal, he will provide what it is here as well. But just know that branch on equal is BEQ and branch on not equal is BNE. And then this is another load type that is 2. So let's do a little bit of math. We do 2, 3, 4, 6, 7, 9, 11, 12. So your answer here is 12. Is there any questions about that? Is there any questions about why that's 12? Alright, are there any questions about... Oh, that actually fell out, damn. Are there any questions about any other question here? No? Alright, so let's compare.
Justin,
Yeah.
if branch is equal, is it one memory or is it's two? If branch is equal.
If branch is equal, then it's still 1, because
Okay.
branch operations don't have a memory stage. You're just taking the value of the label and just incrementing PC.
I think
Okay,
if you
thank
guys
you.
are like, if you wanna make sure, just also write what stages each instruction has.
Yeah.
So just write F, D, E, M, W, whichever one applies, and then just count the Fs and then count the Ms.
Yeah. That's pretty much it. And then for data memory reference count, just count the M's. Don't count the F's.
Yep. Also, only count them if the instruction was actually executed.
Yeah.
If it's not executed, it does not go in there.
Yeah. So like let's say that we had a branch on equal here. Ignore the instructions. Let's say there was a branch on equal here and the label Y was here. And let's say we did that branch. It would be 1 instruction, 2 instructions, 3 instructions, 4 instructions, 5 instructions. And then from that, let's kind of determine what the memory reference count would be. This would still be 1. This would be 2. And then this would be 2. But then we go down to here. This will be 1. And this will be 2.
Wait, no, it's a branch. It can't be two
No,
for
no,
the third
no,
instruction.
what?
The
Oh,
third instruction, if it's a branch, there's no
yeah,
mem.
yeah, I forgot that we're hypothetically putting that as a branch. Right? So that's going to be 1, 3, 4, 5, 7. Right? Because then you would skip these parts here. So your memory reference count would be 7 instead of 12.
And that's because again, I'm sorry, I didn't.
Would you say you I don't know.
What, like, why are you skipping those three again? I didn't hear you before.
Because I said let's assume that that Y label, instead of a Y label, it's a branch to a Y label, and let's say that it's true. And then here I'm saying, let's say that this is the Y label here instead of a branch, right? And yeah, that's why we skip those 3 lines there.
Okay.
That also changes your memory reference string, by the way.
Yeah.
Anything that isn't executed.
Yeah. All right. Is there any other questions about this one? All right. So let's go to the answers. And also, just a word of advice, don't cheat on tomorrow's exam because we all have different values from what he said. So you will get a 0 and then he'll also know that you're cheating. So, yeah. Anyways. So, we see here, he increments by 1 on each part because 8 divided by 8, that's 1. And let's look at his answers. He does 20 and 19. 0, 0, 2, 0, 0, 0, 1, 9, that's the same thing. And then our answer was R1 or 2. He just put 2, so I would just go with 2. And then you see he does operation is the load, source is 16, and destination is R2. That's exactly what we did here as well. where we just restated the instruction. Then we said the operation was load, the operands was the destination, which is R2, and the source, which is 16. And then here he said 23, which is just 0023. And then F he said 12 as well. Right? Any questions about that? So let's do the final exam, and then I guess we can go over some of the problem sets. Okay. So here, it's kind of a different question, right? But he does give us space to write our PC still, okay? So I would still recommend writing it. And it says, assume the following program is loaded into main memory with offset 25. Boom. You already know. 0025. On a 16-bit architecture. Boom, boom, boom. That's 2. We already know that. From there, we could do 0027, 0029, 0031, 0033, 0035, 007039. Again, I just put it by extra because PC always stores the address of the next instruction. Okay. Alright. It says you can assume that each data memory location has value 5. Immediately, boom, boom, 5. And each register initially has value 4. So every register is already filled with 4. Okay. Alright. So from there, it's saying provide value for PC during the decode stage of instruction 5. Right, which we know that decode has nothing to do with PC, so we're going to be referencing the PC value during the fetch stage, right? Or sorry, the end of the fetch stage. So let's go to instruction 5. See, it's an R type, but again, that has nothing to do with fetch. Or sorry, it has nothing to do with PC. We know that once fetch has finished for this stage, that means we incremented it to the next instruction. So the answer here is going to be 0035. Okay. Next it says provide the value for MAR at the end of writeback stage of instruction 6. So let's go to instruction 6 right here. And we're providing the value of MAR. We know that this is an R type instruction because we're loading an immediate value into whatever register, right? And because of this, that means that we never touch MAR past the fetch stage, right? And we know at the beginning of the fetch stage, the value in it is the address of our current instruction. So the answer again here would be 0035. It doesn't matter that we're at the end of the writeback stage, it's just a trick because R type never touches never touches MAR after the fetch stage, right? And even then, that's not the beginning of the fetch
We're on
stage.
instruction 6 though.
Yeah, that says instruction 6.
Oh wait, never mind, never mind.
Then it says provide the value for MDR at the end of exec stage of instruction 3, MDR. That means we are either A, going to be returning a instruction, returning some register, or returning some data. I would go with data, right? Because that's just like with each exam that we've just gone through, the answer is either has mostly been just data, some immediate value, right? So let's go to instruction 3. This is a store type. And we know that in store types, MAR, MAR, that's going to store value 5. Control is going to be set to right. And MDR is going to store, what is it? R2. Right? So it says provide the value of MDR at the end of the exec stage. Right? This is the end of the exec stage. Right here. We're done with exec at this point right here. MDR stores R2. What does R2 store? Well, it says it right here. 25. So the answer here is going to be 25. Are there any questions about that? I see Eric typing. I'm confused with B. PC isn't incremented because R type doesn't touch it. Well, PC is still incremented, but we're asking for the value of MAR, not the value of PC. Right? So at the beginning of the fetch stage, the current value of PC is put into MAR, but at the end of the fetch stage, PC is incremented. That doesn't mean MAR gets incremented because PC is incremented. Why did my shit just turn off? Hold on, give me a second. Sorry, I have low power mode on. Let me just turn that off. Yeah,
Nice photo, bro.
Okay. MAR is the address of the current instruction if it's never changed, right? So for R type, for what is it? For R type, for jump, for what is it? Branch? Does branch change MAR? I don't think so.
No, only if there's an M in the instruction.
Yeah, then it changes MAR. So
But
basically, for
yeah, go
MAR,
ahead.
for R type, for branch type, and for J type, MAR is the value of the current instruction, the address of the current instruction. For S type and L type, that's when it will change. Right? Now let me just find out how to turn off low power mode. There we go. I think I could put that in accessibility.
Only it should be under battery, no?
I'm saying, can't I like make it so I can just go here and then turn it off and not have to go all the way to settings?
You gotta go to you
Hold
gotta
down
do
the
accessibility.
control center buttons, like the apps on your home screen.
Oh, right here.
There you go.
Oh, there we go.
Oh, it's not true that only L and S change MAR. L and S change MAR after the fetch stage. The MAR is updated in every fetch stage.
Yeah.
But the MAR is changed again after the exec stage if you need to go to mem.
Yeah. Basically, the MAR is only changed after the fetch stage in LNS types. That's basically it. Right. You would think that in branch we're dealing with MAR because then we have to go put the label in MAR and then update PC to that. All we're doing is that if it's equal, then we just update PC to whatever that label is. We don't have to store it into MAR and then do it. Okay. Where was I? Okay. So yeah, that's 25. And then it says here, provide value for the Z register at the end of exec stage of instruction 4. So we know with the Z register, we're saying that that means that we're dealing with some R type, right? Because Z is only used when we're dealing with R types. And we're saying at the end of the exec stage of instruction 4. Since we're saying at the end of the exec stage, we know with exec stage of R type, that's when the Z register is filled, and then right back, that's when the register that we're filling is filled from the Z type, right? So from that, we know that if we go to instruction 4, our answer is going to be whatever R2 plus R3 is, because that gets stored into the Z at the end of the exec stage. So we know R2 is 25, but we don't know what R3 is. That's 55. And since we know that we don't know the value at the address, that means it's 5. That means that we're going to be taking 25 plus 5, storing it into Z, and then from there it goes into R4. Okay. So 25 plus 5, we know that's 30. That's put into Z, and then from Z it's put into R4. And it's put into Z at the end of the exec stage, so for this, the answer would be 30, right? Now let's say that instead of exec stage, let's say it said fetch stage. What do you guys think the answer would be?
Can I see the question?
If instead of exec stage it said fetch stage, what would be the answer?
Can you also have the question in frame, as in like the list? Yeah, thanks.
$25, right? Because in this R-type instruction, what it's doing is that in the exec stage, it takes the value 25, puts it into Z, and then from Z, it's put into R2. So at this point here, Z stores 25 until it gets overwritten, which it's not. It's overwritten here at the end of the exec stage of this problem, but it's not saying at the end of the exec stage, it's saying at the end of the fetch stage. So Z has not been overwritten yet, and that's why that answer would be 25. Any questions about that? All right. And then here it says provide the total memory reference count. Remember that we are just providing the amount of instructions, but uh, adding an extra count for load and store. So remember that this is an R type because we're loading an immediate value into a register. So that's an R type, and that's going to be a count of 1. This is an L type, that's a count of 2. S type, count of 2. R type, count of 1. R type, count of 1. R type, count of 1, right? Because we're putting 3 into R5, that's an immediate value. And then branch on not equal, that is a branch, so that is a count of 1. So your answer is going to be 1 plus 2, 3, 5. What the hell? What happened? 1, 3, 5, 6, 7, 8, 9. Your answer is going to be 9. Questions about that? And then total data memory reference count, remember That is just the amount of LNS types instructions in your code. From that, we know it's just where this is not an S type, or sorry, remember this is not an L type, this is a R type, so we wouldn't include that. This is 1, this is 2, and that's it. So your answer is just going to be 2. And then it says provide memory reference string for above looped execution. So basically remember that we're going to be adding something to the memory reference string whenever we're going to whenever we do the, hold on, I gotta sneeze. Sorry. Whenever we do the mem stage, right? So we're not doing mem stage here, but we're going to an address here. So we're going to add that address to this memory string. All right, let me get rid of this brackets. After that, we're going to memory again to address 5. It's going to be 5. And then it looks like we don't go to memory again. So basically with the memory string, whenever you see that, whatever's going to be in there is most likely going to be in our memory string. Now, again, that depends. Let's say if we have a jump here, and then we have a store type here, and then whatever label, let's say it skips it, then this is not going to be in the memory reference string. Okay. Oh, thank you, Eric. All right. So your answer is just going to be 55, 5. Yeah, only if the line is executed. Because it's a string of memory that we've referenced in our executed code.
What about if there's a loop?
If there's a loop, then let's say there's one memory reference here. There's a label here, memory reference here, and then a jump to label Y. So I mean, yeah, this is an infinite loop here, but this is just to give us an idea. And let's say this is 55 and 5. Then your memory reference string is going to be 55, 5, 55, 5, 55, 5, 55, 5, dot, dot,
Are you
dot, dot.
sure?
Yeah, because it can
Because
repeat.
I thought the point of the memory reference string was to figure out if it's for the cache, right? You're trying to figure out if the data has changed. Why would you have like a long ass string when your data hasn't changed? In this specific example,
Because we're
where it's
also
a
checking for hits and misses, right? Where if we get an address, we put it into memory reference string, we go to the cache, and we check if the latest address in our memory reference string is inside the cache. If it's not, that is a miss. If it is, then it is a hit. Right? So stuff in the memory reference string that can repeat. Cache, it doesn't repeat. It's just one position where it's gonna go, and then we check if it's a hit or miss. But memory reference string, it can repeat. And that's just saying that's just saying in our executed code what addresses have we referenced. That's basically all it's saying, and it's going in sequential order.
okay.
You'll see in that one of the answers to the problem set, I think problem set 5, I think like 2 of the addresses repeat, something like that. Any question? Oh, I saw. Oh, let's see. Eric had a question. Another question about B, but if it said provide value PC during decode, for example, then it would be 0037. For B. Oh, for PC. Yeah. It'd be 0037. Because at the end of fetch, then you increment PC. And then once you're at decode, that means you already incremented the PC. And the incrementation would point to the next instructions. That'd be 0037. Any other questions about this one? Alright, I guess we'll head over to the problem sets. Alright, so this is just RTL. We're very lucky because he doesn't make us write MIPS. If we did have to write MIPS, we'd probably all fail. So first, we're saying A is equal to B minus C. We know for any arithmetic, we have to be doing it with either an immediate value or a register. But here, these are just addresses, right? So first, we have to store these values in addresses, do the arithmetic, and then store that value, okay? So first, what we can do is we can take register R2 and have that store B. Make sure to put the brackets. From there, we can take register 3 and have that store C. And let's take register 1, have that store R2 minus R3. So basically, R1 right now is equal to B minus C. Right, because B minus C is just some address, but then when we put it into a register, then the register stores the data inside the address, not the address itself, the data inside the address. Okay. And then from there, we haven't set A equal to R1 yet, right? So we could simply just take A and put R1 into it. Again, this is not changing the address of A, voice correct. They're not changing the address of A, we're changing the data at address A. And that is finished. Any questions about that? Alright. Here, similar, we're doing the same thing. R2, putting D, R3, putting F, R1, we're putting R2 plus R3. And then R1. Oh, sorry. No, then we have to set register E to R1, right? And that finishes this line. Then we're
Yo,
saying
your stream froze.
7.
Your stream is like frozen.
Oh shit, hold on. It's probably because oh my god, my iPad is so hot. Let me see, share screen. See now?
Yeah, it works.
Okay. So what I was saying is that this code here that we just wrote executes this right here. Where we took R2, put it in D, took R3, sorry, took D, put it in R3, took F, put it in R2, sorry, took D, put it in R2, took F, put it in R3, then we took those two, added it, and put it in R1, and then from there, we set that value equal to the data, sorry, we set the data in E equal to that value. Okay. I would say don't forget to do this, because if you just move on to the next part, then you're not doing this part. We're setting E equal to that. From there, we're saying E minus 2. We're saying E is equal to E minus 2. We already know the value of E. It's already in R1. So we can just update what R1 is if we wanted to. Or we can do it with a different value. Let's just do it the easy way. R1 is equal to R1 minus the immediate value 2. And then we just put E again. How come you're not including the square brackets for DNF? Oh shit, yeah, I forgot. Okay. Any questions about that? Alright. Alright, and then this is just the system again. That's so here it's saying for a 32-bit system, provide the value of PC in physical memory if OS loads a program at offset 0022. Again, offset that starts at 002. And this is a 32-bit system, so we're gonna do 32. Divide that by 4. That is 8. Sorry, no. Stupid. My brain is farting. Hold on.
Divided by 8.
Yeah, divided by 8. Okay, sorry, not 8. Not divided by 8, but it's equal to 8. Okay. 64.
Justin, is 32 divided by 8, which is 4.
Oh, no, sorry. Yes. Bro, I'm sorry. I'm so tired. Okay. 32 divided by 8. That is 4. I got these messed up. Okay. So we're incrementing by 4. That's just 0026, 0030, 0034, 0038, 0042, 0046. Any questions about that? Again, please don't make the same mistake I just did. Write that down in your books. The number of bits divided by 8 is how much you're incrementing by.
You said it wrong again. Wait.
No, I didn't.
No, never mind.
Yeah,
I'm confused this time.
yeah. Number
Fuck
of
me.
bits divided by 8 is how much you're incrementing by. Okay. Alright. Problem set 2. Saying provide the type of instruction and all stages for each of the following instructions. This right here. This is a load. We're taking data from address and loading it into the register. This right here, this is an R type. Values, doing some arithmetic on it, and storing it into a register. This right here is a store. Taking some value from a register and storing it at some address in memory. This is just a jump, meaning we're jumping to some label which contains an address. And then here, this is just a store. He said don't let the font fool you. That is just an error. So, yeah. Alright. And then it says provide all the stages each of the following instructions. We know load. That is fetch. Decode. Exec. Write. Okay. R type is fetch. Decode. Exec. Store. Fetch. Exec. Jump. Fetch. Code. store is fetch. Sec. Right. Are there any questions about this part here? Then we're saying provide the total memory reference count. Okay. Instructions, meaning this is just the fetch stage. Plus map. Okay. For above execution. This is a load, so that's 2. This is an R type, that's 1. Store, 2. Jump, 1. Store, 2. That's 2, 3, 4, 5, 6, 7, 8. Now, we don't know where this label X is, so we didn't skip this one here. Because they can also, it could have also been, you know, here, something like that, and then we would have had an infinite loop. So we don't exactly know where label X is, so we just included this in our memory count. Let's say label X was right here. You would have skipped this, and it would not have included it in the memory reference count, and it would have included this and whatever was beyond it. So the answer here is 8, but understand why it's 8, and why it can be some other answer. Okay. Any questions about that? Alright. After that, we're asking to provide the total data memory reference. Again, that's just the amount of times that we have a mem stage. Right? We have one mem stage here, one mem stage here, and one mem stage here. So the answer will be 3. Now it's saying provide total execution time given following stage execution time. Remember, Vivek knows that you are bad at math. Do not put a final arithmetic answer. Just put the formula and just say add it, and he will give you the credit for it. Do not give a final answer of like 400. Just show the math and then just box it, I guess, right? So this is a way of showing the math. We have 2 load types. Sorry, no, we have 1 load type. We know the load type is fetch, which is 40 nanoseconds, plus decode 10 nanoseconds, plus exec 10 nanoseconds, plus mem 30 nanoseconds, plus write back 10 nanoseconds. Plus, we have 1 R type that is fetch 40 nanoseconds, plus decode 10 nanoseconds, plus exec 10 nanoseconds, plus write back 10 nanoseconds. Plus store, there we have 2 stores. Store, that's 2. We have 40 nanoseconds plus 10 nanoseconds plus 10 nanoseconds plus 30 nanoseconds. And then we have 1 jump that is 40 nanoseconds plus 10 nanoseconds because it's just fetch and decode. That is it. You can leave this as your final answer. If you want to, you can do the math, try to figure it out. But if it is wrong, you will get the answer wrong, even if you did this correctly. Right? I don't remember what the answer was. It was like 400 something. But let's say you put 500 by mistake. He said you will get the whole thing wrong just because you don't know how to do math. Okay. So please, this is the final answer. Leave it as so. Trying to ingrain this in your brains. Please do not try to add it out. Okay. Any questions about that? Shane, you were the one that wanted to do problem set 2. Was it a specific reason why problem set 2, or were you able to answer it? Answer your own question from us doing it here? No question. You just want to see how it's answered. Okay. Problem set 3. We're saying for following program executing on a single cycle processor, right? You can mean that means that each instruction just has one cycle. I think that's what it means. I don't know. Or I think it can only run one cycle at a time. It's saying you can assume that each memory location contains value equal to 2 and each register, if not provided, is initialized to 1. Okay. This is basically what we're answering on the exam. So we're saying provide total instruction memory reference count for above execution. Let's see. We have a loop here. This is set to 100. This is set to 0. Within here, we're saying R5 is R1, which we don't know what that is. So it says you can assume that each memory location contains value 2, and each register is initialized to value 1. Right? So each memory contains 2, so R5 should be 2, I believe. And then we're saying R4 is R4 plus R5. R4, we don't know what that is, so that's just going to be 1. So 1 plus 2, R4 is 3. Then we're saying R6 is R2, which we don't know what R2 is, so that's just going to be, what, memory location 2, so R6 is 2. Then we're saying R4 is R4 minus R6, that is 1. And then we're saying R3 minus R3 minus, we're saying R3 is R3 minus 1, so that is just 99. And then we're saying branch and equal R3 to 0, that's false. So now we're able to realize that everything we just did here was just a bunch of baloney. And what really matters is this line right here, right, where we decrement, and then we're checking at this point here, right? So we're saying we're going to branch if R3 is, wait, branch on not equal. Wait, oh yeah, so if R3 is not equal to 0, then we go to loop, which is right here. So when R3 is at 99, R3 is not equal to 0, so then we go up. And we're going to keep doing this until R3 is equal to 0. Now, it kind of seems like there'd be 101 loops here. But just think of it as a for loop going from n to, think of it as a for loop doing int n is equal to 100, n is greater than or equal to 1, n minus minus. I guess you can kind of think of it like that. Not greater than, yeah, greater than or equal to 1. You can think of it like that, and then it would run 100 times. And it gets out once it's equal to 0. So from this, we know this loop is going to run 100 times. We know this part here is just running 2 times, right? Well, not 2 times. It's like one instruction here, one instruction here, then 100 instructions here, basically. Okay. So we're saying provide total instruction memory reference count for above execution. Okay. So since we're saying instruction memory reference count, I believe that's just the number of instructions, if I'm correct, right? So we have 2 here, then we have 6 here, but that's running 100 times. So that's 600 here plus 2, that's 602. So answer here would be 602. Okay. Because it's not saying total memory reference count, it's saying total instruction memory reference count, which I believe that just means the amount of instructions in our program. Okay. And it's saying provide total data memory reference count. That's referring to how many load and store instructions that we have. So if we check, we have one here, and that's it, but it's also in the loop. So we have 2 instructions that are happening 100 times, so that's going to be 200. They were saying provide total number of cycles for above execution. Cycles meaning how many times an instruction is executed in our program. That will just be 602. Then CPI, again, we remember that it is the number of cycles divided by the number of instructions executed. Damn. Which is equal to, we have the number of cycles at 602, and the number of instructions is 602. So your answer is 1. And since we are on a single cycle processor, the CPI is always going to be equal to 1. You just have to be able to show what is being divided, right? But the answer will always be equal to 1.
Could you explain the 200 again?
200, it's saying for the data memory reference, right?
Yeah.
Basically saying how many load and store type instructions are we executing here. And we see here we have 2 load and we have 2 load and store. Sorry, we have 2 loads, no stores. And those 2 loads are inside of our for loop, which runs, or sorry, not our for loop, our loop that runs 100 times. So from
Got it.
that means that together there's going to be 200. These L types are going to run 200 times.
Got it.
And that's why it's 200. Alright, and then we can just double check it that that's correct. Go to problem set 3 solution. 602, 200, 602, 602 divided 602 is 1. Damn, why is that happening? Holy crap. Alright, any questions about that one? Alright, problem set 4. It says consider given code with following time taken. For each instruction, stage fetch is equal to 100 nanoseconds, decode is on to 25 nanoseconds, execute is 100 nanoseconds, memory is 300 nanoseconds, and write back is 100 nanoseconds. We have to calculate the total execution time for the program execution. Right. So I think, what is another word for that? TMA? What is it? Total memory? I don't know. I don't know what it is. But anyways, I think we learned it when we were doing cache, but that's just another word for it, I think. So let's grab this. Obviously, we are going to be doing some math here, but again, we are just going to be writing out the calculations. We're not going to calculate it ourselves. So we have here, have an R type, have a load, have an R type, with load, have a load, have a store, we have an R type, a load, we have a load, another R type. Okay. So in total we have 1, 2, 3, 4, 5, 6, 7 loads. right? 5, 6, 7. 7 loads. Then we have 1, 2, 3, 4 R types. And for S type, just have 1. And we know for for load, we know it's fetch, decode, exec, mem, write. And we've been given the time for those. So fetch is 100. Decode is 125. Exec is 100. Mem is 300. And write back is 100. Okay, so this is for load. Then R type we know is fetch, decode, exec, write back. So that's going to be 100 for fetch, 125 for decode, 100 for exec, and 100 for write back. Then store we know is fetch, decode, exec, mem. That's just 100 plus 125 plus 100 plus 300. That is your final answer. Okay. Are there any questions about this? Right. And then again, we could just double check that we match up with our solution. 7 times 1 times 4, and that's exactly what we did. See here, he listed out the stages of it again. Okay. All right. Problem set 5. Last problem set on the exam. My brightness just go low for, I don't know. Problem set 5, we are not, cache is not in the exam, so we can just take that out. Let's deal with problem set 5, part 1. Right? So remember, when we go to the mem stage, that is when we are going to add something to our memory reference string. What that is whatever is in the MAR. You can think of it that way. Right? So in the first part, we have a load which goes to the main memory with address 2. So in there, memory reference string, we will put 2. Next, this is an R type. We don't go to main memory, so we go to the next part. This is a load type, address 5. So we're going to put 5. Cross that. Then we're going to, oh, sorry, no, we don't cross that. Put a check mark. This is an R type, no mem stage. This is a load type, we have a mem stage. Okay. And we're going to put 7. From here, we have another load type, but it has address R4. So remember that when we have a register and we put brackets around it, we're referencing the number inside the register, right? So let's say register R4 contains the value 7. If we're doing R4, that is saying we are doing address 7. Right? So here, there's two possible answers that you can put. You can either one, just straight up put another 7. That's what we're referencing. Or you can put this instead. Right? I believe either would be sufficient. Actually, wait, no. No, apologize, I apologize. This would be the answer. You can't just put 7 because, yes, we store R4 with address 7, but we don't know the data inside of address 7, right? So this doesn't mean that R4 contains 7. That just means that R4 contains the data inside 7, which we don't know. So when we call brackets R4, we don't know what R4 is. We can't just say brackets and then whatever number that may be because we don't know the number. So instead, we would have to put brackets R4, right? And then here we have another instruction that goes to memory. This is the S type. And here we are dealing with address 8. Let's go here. Address 8. Nice. Then we have an R type that does not go to main memory, so we cross that out. Then we have an L type that goes to main memory to address 2, so we can put a 2. And you can see that just like we were talking about before, the memory reference string, it can repeat, okay? Because we're just going in sequential order and then we're adding it to the memory reference string. Then we're gonna add 6 because this is a S type and low type, and it goes to main memory. Then we're gonna add 4. And I'm not gonna add anything else because this would be an X, right? Because this is not going to main memory, right? And this would be the final answer. How did it become an oval? Right. Is there any questions about this? Questions? I see KT typing. Oh, not a question? Okay, yeah, you're welcome. And then we could just compare that answer to what we have here, which it is not there. So again, let's just do the hack. Go to let's choose list at 4. Go here. Oh, what just happened? Go here. Boom. Change that to 5. And we see 2, 5, 7. We see that 2 repeats. 2, 5, 7, R4, 8, 2, 6, 4. 2, 5, 7, R4, 8, 2, 6, 4. Okay. So this is the correct answer. Alright. Again, are there any questions about this? Now's your chance to give any questions. I'm not Vivek, so you will not be yelled at. Alright. Should be it. Is there anything else that you guys wanted to go over? Basically, I think we basically went over everything. Tomorrow, so tomorrow I'm taking psychology, so I have to do like a study from 12 to 1:40, I think, in the science hall, I think. So then I'm gonna do the study from 12 to 1:40, and then I'm gonna go to 3:20, at the 140 session. I'm just gonna go then, so it ends at 3, and then after that, we can study from 3 to 6:30. Yeah, that makes more sense because if I went to the later session, I would end 320 at 425, and then we'd have less time to study. Where can we meet? Same place in library? Which one? Floor 1 or floor 2? Yesterday. I think y'all should check out the music hall first to see if that is open, like the whiteboard room in the music hall. I feel like that'd be better to use. And if not, actually, I think doesn't I don't know what time that closes actually. Not sure. So I guess we'll just do the library. What Casey's talking about, if y'all want to do another study session tomorrow at 3, go to the library floor 2. So you're just gonna go down one level once you enter from floor 3. You're gonna go down one level and then you're gonna go to the seats near the bathroom, right, KT?
Okay. Could you just go over problem set 3, the second part, just one last time, if that's okay?
The 200, right?
Yeah. No, the 602. So that's you're looping the program and you have 100, right?
So
The
you're
first
saying,
602.
oh, okay,
Yeah.
okay. So yeah, this is just saying instruction memory reference. We're not saying total memory reference. If it was total memory reference, it would be more because we
Mhm.
have load and stores. That accounts for 2. So that'd be more. But we're talking about total instruction memory reference count, meaning just the amount of instructions in our program that are being executed. So the first 2 lines are just 2 because they're not a part of the program. Sorry, they're not a part of the loop. And then this loop has 6 instructions that run 100 times. Right? So from that, that's 2 plus the 600 instructions. That's just 602. That's
Got
why the
it.
answer is 602. And then here, number of cycles, that's 602 because we have the amount of cycles, meaning fetch, decode, exec, mems, right, or wherever. That's 1 cycle. But also fetch, decode, exec, write without mem. That's also 1 cycle. Or fetch, decode, exec, write without mem. That's 1 cycle, right? So basically, total instruction memory and the number of cycles in this question are the same. And then for CPI, it's just the number of cycles divided by the number of instructions, which is 602 divided by 602, which is 1.
Got it. Thank you so much.
Yep. Who said it? Shane, I thought you said you had markers. Who has markers? Someone could bring markers, that'd be great. Markers and an eraser. Bro, why the fuck we bring up Bob the Builder? um, alright. Hold on, let me grab a drink of water. Alright. I'm not sure what else that we really need to go over. I don't know what bro's talking about. Is there anything else that y'all had to like go over or like past exams, anything like that? I don't know. Maybe we could do past exams tomorrow from that Google Drive we have. I guess we do that tomorrow, but I don't know. Sir, yeah, okay. I guess we'll just do that. But I guess tonight, after this, write stuff in your notebook. So write down incrementation. That's the amount of bits divided by 8. Write that down. Write down each cycle for each instruction type. That's load. Load is fetch, decode, exec, mem, write. Store is fetch, decode, exec, mem. R type is fetch, decode, exec, write. Branch is fetch, decode, exec. Jump is fetch, decode. Um, Write down the amount of time he gave us for each instruction. So I think it was that fetch was 35 nanoseconds, decode was 2, exec was what? I forgot. Exec was 2. It depends on the instruction. Mem is 30. Write back is 1, I think. You said branch is FDE and jump. Yeah, because branch you have to. That's when you're doing the comparison in the AOU in the exec Yeah. Um, and then the exec and branch that can differ by 1 nanosecond, because if it turns out to be false, then you don't increment. But if it turns out to be true, then you increment PC to whatever label it is, and that's 1 extra nanosecond to do so. Um, and then so yeah, write down your stages. Write down that load immediates are I types, not L types. So like if you're doing register, if you're doing a number into a register instead of a register into a register, that is a R type. If you're doing a register into a register, is that an R type? I don't remember. That's an R type, right? Because an L type is an address into a register. Yeah, so yeah, write that down as well, that a register into a register is an R type. And a number into a register is an R type. But a address into a register, that is an L type. And a register into an address, that is an S type. Okay. What else can you guys write down? Let me see.
We can bring like old exams, right? I printed
Yeah,
them
you
out.
could
Like,
bring anything, you just can't use your phone.
right, okay.
Can't use your phone, can't use your calculator. I guess write down how to do memory reference string. Write down that data memory reference count is just the amount. Data memory reference count is just the amount of load and store instructions. Total memory reference count is the amount of instructions, but 1 extra for load and stores. Um, Write down that Z register does not empty after an R type instruction. Uh, Write down that PC always points to the next instruction. Remember, write down how to get operations and operands. This. Like I said before, write down your stages. And then also write down the formula for CPI. Number of cycles over number of instructions executed. That's your output. And remember, if he says show your work, show your work. Write down the formula, enter it in, and then put your answer. Okay. Let me see if we do your. Oh, yeah, we did this as well. Where we said if this is a 64-bit, that's 64 divided by 8, so you're incrementing by 8. So let's say we start at 0016, increment by 8, and you go all the way up into 0112, because you go up to 0104, and you go up by 1. What else? Pretty much it. If you understood everything we did today, then you should be fine. But again, if you are still iffy on something, please ask me. Don't wait until tomorrow, because if you have one question, like Vivek says, if you have a question, someone else probably has that question. Questions about this, or should we continue this for tomorrow? Oh, damn, just got deleted. Alright, that looks like there are no more questions, so that should be it. So I guess I will see you guys tomorrow. Good luck. gonna be in the library at, let's say, about like what, like 3:10. Get there. Yeah, no problem. It's so I'll say about 3:10. Um, and yeah, I guess remember before you go to sleep, print out your problem sets, do them so you can have them on the exam, and also print out the past exams, do them, and then you can have them on the exams as well. Put little notes to answer like why that's correct. Um, and then tomorrow, I guess we'll just compare notes. Uh, if someone else wrote something that you forgot, you can, I guess, remember to do that. Shit. The recording, let me end the recording.